Cool. 62 unique paths. The robot is located on the top left corner of an M by N grid. The robot can only move either down or right at any point in time. The robot is trying to reach the bottom right corner on the grid. How many possible unique paths are there? Um, okay. It's a little. So actually, I mean, this is actually a very straightforward, I want to say, dynamic program problem. And it's not straightforward in the sense that it's, uh, easy to come up with. It's just very standard in the sense that it's a very possible textbook type algorithm. Yeah, like, yeah. My only concern, unless I'm missing something, is kind of like what happens if the number gets too big. Because usually with M and N is 100, unless I'm missing something. Right. Then yeah, down right. Yeah, unless I'm missing something, like you could definitely overflow long or int or long very quickly. And actually, there's I think the thing to notice here is that it's actually, I mean, once again, this is a straightforward-ish, quote unquote, dynamic program problem, which stems from uh, uh, what was I gonna say? I mean, it's very textbooky in a sense once you kind of get it down. But the other fun thing about this problem is that it's actually related to how you calculate binomials in the sense that this is where I wish I could draw. But binomial type things, and I'm gonna try to attempt some ASCII art. So bear with me for a second. But let's say you have a top thing. Oh yeah, so then binomial is x, and so you have like the top layer, and then you have the what is it called? Uh, like 1 plus x to, I forget. Oh man, I don't remember my mathematical formulations, to be honest. But yeah, but on the next level, huh, it's 1 plus x, and then on the next level is 1 plus 2x plus x squared. Whoops. Um, and then so forth, right? I mean, the expansion for that, kind of, or at least familiar with it. And you get this. So that's kind of like, I mean, you could keep on drawing this. This is where, like, I don't know, you learn it in not one of the grade schools, or maybe high school. I don't remember anymore. And that's just like, and actually, I think that's why I messed up. So one on top, and then this obviously just corresponds to 1 plus x to the 0. This is 1 plus x to the first, and then this is 1 plus x to the second, and so forth, right? So then that's kind of the pattern here. And it turns out that this thing also is a way to kind of like, I think they're called something like generating functions. Sorry, this is like a decade of math ago. Hey, thanks for the follow, Hemstripe. But yeah, but that's the general thing here, and that actually, and you could, and the kind of the standard way to explain it is that, and you could, I forget what that primit is called. I mean, I just think of it as binomial, but I think Pascal's triangle. That's what I'm thinking of, right? And this is a Pascal triangle thing where you could think about it as one and then one and then 1, 2, 1. Same pattern essentially what I did before, and where this node is just the sum of the two entries in the row before, and so forth, right? Dot dot dot. So this is Pascal's triangle, which relates to this other thing that I guess I should have started with the Pascal triangle, but I just was blank on the name. But anyway, so the fun thing about this is that this is, if you kind of tilt the board a little bit, or like if you look at it in a diagonal way, now now you can see your entries are actually like one on the first row, one in the first column, and then two, three, oops, three, and so forth. Right? And then if you tilt your head a little bit, you could get like the diagonals. So this maps to these in the diagonals, right? I don't even know how to draw this on ASCII art, but like diagonal for the first row and or first diagonal and so forth. So those are your things, right? And also, the fun thing is that this is also the number of unique paths, because you could look at each node to be like, okay, how many ways do I get here? Well, there's one way to get to this cell, and there's one way to get to this cell. So there's two ways to get here. And then how do I get to here? Well, there's two ways to get to this cell, and there's one way to get to this cell. So now there's three ways to get to this cell, and so forth. And anyway, so there's all these math things. So anyway, there's a very long explanation. Hopefully it's kind of interesting to y'all, but it's a long way of saying that's how you would solve this problem in the same way. And it relates to binomial and Pascal's triangle and all these other fun stuff. But one more thing that I'm going to leave you with this problem then is actually another kind of interesting thing is if you sum up the rows in Pascal's triangle, which is also diagonals. This is actually, if you sum it up, is 2 to the 0. And if you sum this up, it's 2 to the 1. I mean, you could see that easily. And then here is 2 to the 2 and 2 to the third and so forth, right? And you could kind of make this proof the other way very quickly, because for each entry in the previous row, you're gonna, for each of those paths, there'll be two paths out, right? So you always double the paths every time, right? So so on each row, the sum is 2 to the k or whatever. So that's kind of one interesting thing about it. And that also goes back to, there's another way to prove this, with another way to kind of visualize it with binomials, because with binomials, another way to think about it is like this entry is also the number of ways to choose given 3 elements, choose 1 element, right? This is given 3 elements, choose 0, 3 elements, choose 2, 3 choose 3, right? And summing, so that's, yeah, so it's 3 choose 0, 3 choose 1, 3, and then you sum all that, should be 2 to the k, because that's literally the number of possibilities you can have, because that's just, like the in-out counting type thing, right? Anyway, so that's a very long-winded way of saying, but the reason why I kind of brought this up, and not just to flex or show off or whatever, is that it's something that I think about when I see this problem, because when m and n will be at most 100, what that means is that, so like, this, let's say this is row 100. I mean, I skip ahead a little bit. So like you have this entry here. So yeah, dot, 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 m or n, I forget. That's not really, I guess we should check which. And then like in the corner here is m plus n, right? And the thing here is that, as we talked about before, so this is at most going to be m choose, oh sorry, m, this is m plus n choose, is it? No, what is that row? I guess that row is m plus, well, that diagonal is m plus n. Choose, oh wait, what? No, the sum of that one is, I don't remember. Man, I'm mixing myself up. It's been a while. But the point is that this is dominated by like the sum of that diagonal, if you will. Oh yeah, wait. Oh wait, no, because okay, I'm thinking of this Sorry, I was doing the math for this place. where it has to be between m and n, some x. But if you're doing like diagonal, then m plus n is on the on this diagonal, which is, yeah. So it's m plus n choose, no, it's m times n times choose m plus n. I don't know, but the point is that this has a bound of like something like 2 to the m plus n, and that was what concerned me when I saw that m plus n would be 100, because you get a really big number is my point. So, and looking up and down, my other thought about it is to see if they have any constraints to be like, oh, hey, but it's okay because, it's between 100. Or sorry, if the answer is like, the answer will fit in long, or 64-bit int, or a 32-bit int, depending on how they want to do it, is usually something that they would tell you. But anyway, so given that all set, this is, that's why this dynamic programming problem is a very straightforward dynamic programming problem in this sense, and then it's just about coding it up. So I'm going to do that. Yeah. Okay. And there's a easy optimization that I'll talk about, but I'm not going to do yet. I did it last time, so maybe I should do it. I've been trying to do it more, but I'll just do the obvious thing first. And set the corner to 1, and then now for x and yes, it doesn't actually. Well, okay, fine. Just bound checking. Is that right? No. And then now we just have to return. Oh god, maybe it's off by 1. I sometimes I have off by 1 on these things, but yeah. Oops. Where did I get D from? Sound. Oh, what? Yeah, let's try a real number for Kixies. Oops. I mean, in Python, I think I don't have to care, but it just, in other languages, it's a little weird that they don't specify it. Especially in JavaScript, for example. See, there's a very long number. And I guess they don't have an expected result because it crashes on it. That's why you need to specify your things. What should I miss? A silly case. Okay, cool. Yeah. So again, this is very straightforward, but that's how I kind of think about this problem. And these things are kind of fun to kind of think about because it comes up in random places as well. Oh yeah, the other thing that I would say, a very common thing is to refactor this is that, well, this is a dynamic programming problem, obviously, of m times O of m times n, and with O of m times n space as well. But the thing is, you actually reduce this to O of m, or O of min of m or n, by noticing that if you look at this array, you actually, which is this array here, essentially, pretty much, right? So now 2 will always look at 1 and this 1 and so forth, and then sum them. 3 will look at the 2 and the 1 and then sum them and so forth. And then now, like, we go all the way down, and then now, so for example, 4 and 5, say, Well, the thing is, at the 4, you notice that you only add the 3 and the 1, right? So actually, in this entire row, oh, well, let me add some dots. In this entire row, you only care about the results from the previous row, right? Um, so this row only calculates itself from this row. So actually, if you kind of take advantage of that, you could actually just get rid of all these stuff. Well, not get rid. I mean, maybe get rid of, but you could. You don't have to think. You don't need that memory to stay around unless you need to look up stuff for whatever reason in the future. But yeah. So if you notice that, then actually you only need to keep track of the last 2 rows or so, or the current row and the previous row. So you could actually do that in linear space as well, because yeah, it's like when this is done, then you just keep track of the new one and so forth, right? Anyway, so that's the how you solve this one. I would say for dynamic programming problem, this is way fundam- this is a way one of the more fundamental ones. So definitely get familiar with it. And I heard that Google still asks a lot of dynamic programming problem. I actually, well, I haven't interviewed for Google for a long time, but that's what I've heard. But in other interviews, I feel like people have not been asking dynamic programming problem. Uh, so so yeah, maybe it's a. But yeah, if you want to go to Google, I guess you should study dynamic programming. But yeah, that's what I have for this one. Cool.